Okay. If anyone hasn't turned in homework number 7, certainly you can turn that in this morning. Okay. And then I will be grading it tomorrow. And then that other homework 8, that's due on Friday. Okay, so today we're going to take the big plunge and talk about triple integral. So in this case, we're having functions of up to 3 variables, okay, x, y, and z, and we can define triple integrals. All right. The easiest case is when, so we're going to be integrating over x, over y, and over z. Not necessarily in that order, all right? The easiest case is when x just goes from one number to another number, y goes from one number to another number, z goes from one number to another number. That's the easiest scenario. And that's what we can call a rectangular box. If B equals a rectangular box. All right. In other words, B is equal to x going from A to B times times y going from, say, C to D, and Z going from maybe R to S. X, Y, and Z. All right. So what we're integrating over is just some kind of box in 3 dimensions. In this case, now we're going to have 3 integral signs, not just 2. So 3 integral signs over this solid rectangular box B of f of x, y, and z. Now we're going to have dv. V suggests volume. So that's the common notation that you'll see for this, dv. This is going to be equal to an iterated integral. And so it's just going to be, say, x going from A to B of our function. That would be, say, our inside integral. And then outside of that, we would have y going from C to D. And then outside of that, we have z going from R to S. And again, we start from the inside out. Okay. And so on the inside there, where we're integrating with respect to x, the other 2 constants, the other 2 variables are treated like constants. So y and z are initially treated like constants. Okay. Now the thing is, Fubini, as long as the function is a continuous function, we can do this order of integration in other orders other than x, y, and z. So this triple integral could also be written, say, as let's first integrate let's put the outer one as A to B dx, and maybe the next one would be R to S, and that would be dz, and then the inside one could be C to D, and that would be dy, and then we have our function here, f of x, y, and z. All right, so we can integrate in any order as long as the function is continuous. And then in this case, our inside integral, we're integrating with respect to y. Of course, we start here. And so in this case, then, x and z are initially treated like constants. Okay, so would that all the cases were over rectangular boxes and then life would be easier, all that good stuff? Well, the more complicated cases is, of course, when we don't just have a rectangular box. So let's put it this way. For what we're going to look at, there are three types of quote-unquote more complicated cases where B is not just a rectangular box. Not just a rectangular box. All right. Okay, and these are all related to the fact that we have three variables, x, y, and z. Okay, and I've got some pictures here to show with this. The first case is where is where z ranges between two function values, two functions of x and y, okay? The first case is where that variable z ranges from I'll put this in parentheses, a low function. We can call it u sub 1, and this would be a function of x and y, and it goes to a larger or greater function. We'll call it u sub 2 of x and y. All right. So let's just look at a couple of pictures here with this. So here's this e here, they're calling the solid e. So we're integrating our given function f of x, y, z over this solid region, e. Now, notice here with this solid region, E, can be looked at, in this case, as here's the z-axis, as z having a top value of some function of x and y, and then down below here at the bottom of this solid, z has a lower set of values composed of another function of x and y. So z ranges between u sub 1 xy up to u sub 2 xy. Then this whole solid that's kind of like, in a way, suspended in midair, however you want to conceive of it, has a shadow that goes down. Think that it's high noon on the equator on the spring equinox or something, okay? The sun casts a shadow straight down. You don't have a shadow theoretically, all right? So this shadow actually of this thing goes straight down, perpendicular, all the way to the, in this case, the xy axis. So, and it casts this shadow of this flat area on the xy plane. So how we integrate this is, first of all, our inside integral is going to be with respect to z, dz. And we're going to go from z, from the lower value to the lower function to the higher function. Okay? U sub 1 to u sub 2 xy. And then outside of that, we have to then integrate with respect to our other two remaining variables, x and y. They're going to be integrated over this region D that's in the xy plane. This has a formal name. It's called the projection of the solid onto the xy plane. It's its shadow. All right. So we would first integrate with respect to z, and then we would deal with integrating with respect to, in this case, x and y. All right. Now, that's the first case. Now, let me give a little bit more detail here with this first case. And then we'll go on to look at the other two cases, and then we'll look at some examples. So I'm going to give you kind of the general stuff first, and then we'll look at specific examples. Okay. So this first case, we have integral, put z equals u sub 1, x of x and y. Z ranges up to u2 of x, y. Here's our function, x, y, and z. And we're first integrating with respect to dz. Then over here, we're going to then be integrating over that shadow, that projection region of d. What we need to do, so how do we figure this thing out? What we have to do is transform this into an iterated integral, where each one of the integral signs has some bounds of integration. Okay. So we have to convert this into an iterated integral. Now, and that just means that each integral sign has bounds of limits of integration would be better. It has limits of integration. All right. What you need to do here, 99% of the time, is you need to analyze this region D that's in the XY plane. The shadow of this is going to be in the XY plane. Now, by analyze, what I'm really saying here is sketch. Okay, that's the initial thing you would want to do. So what I'm just drawing here is an XY plane. And let's suppose that the shadow of this looks like something like this. Oops, straight line. All right. Okay, so what we have here is x goes from, say, A to B. Notice we just have these straight lines there on the left and the right. But y is ranging between two functions of x. This would be, say, y equals h sub 2 of x. The big one down here, this would be y equals, say, h sub 1 of x. All right. So we have to determine by sketching that D area, we can get those other two limits of integration that we need for x and y. Okay. So in this case, if it were something like this, what would in that D region, which variable would I first integrate with respect to? Would I integrate first with respect to x or with respect to y first in this scenario? With respect to y first. Y goes, I can draw an arrow here that's completely within the region. Y goes from h1 to h2 of x. All right. So let's rewrite this integral here. We first have our inside bounds, u1 of xy, z equals u2 of xy. Here's our function. We're first integrating with respect to z. Now we can fill in these other two bounds. We're going to do y next. So let's put dy over there. And y is going to go from the lower one, h1 of x, to the upper one, h2 of x. And then we integrate with respect to x. So you build this thing out like adding on layers to something, however you want to look at it. And then for x, we would integrate from the number a to the number b. Okay, and then this is what we would work with. Okay, going from the inside out. What I want to point out here, and I'll point this out again, look at these bounds of integration here. Notice, remember I said always we're going to have the outside bounds are always going to be numbers. And that's what we have here. A and B are numbers. But we have two other bounds of integration here. The inmost bound for the z potentially goes from a function of x and y to another function of x and y. All right? So the inside, our limits, can be a function of up to two variables. Now, it doesn't always have to be all two variables, but it can be a function of up to two variables. Then our middle limit here can be a function of up to one variable. So we're going to lose a variable here. So here the limits are a function of up to one variable. And then, of course, the outer limit has no variables in it. It's strictly a constant, right? Okay, this is one scenario where z goes from a lower to a higher. We could have another scenario in which when we look at the d region in the xy plane, we have to integrate in the other order because it's oriented the other way. So I'll just get that up here. So we can put this as another possible scenario. Okay, so here again, we're talking, let's see, that's that one. Right. So here again, we're talking about z going from, say, u1, some function of x and y, to some upper function u2 of x and y. And that's dz. And then we have this integral, double integral over this region D. And again, this region D is going to be on the xy plane. Okay, again, we have to convert this into an iterated integral to be able to evaluate this. All right, and again, we need to sketch. Let's put sketch and analyze, because you have to do more than sketch it. You also have to look at it and figure out which is the right case, okay? Sketch and analyze D. So in this case, let's suppose, here's the xy plane. Let's suppose that D now looks something like this, where y goes from a constant c to a constant d, and x goes from a smaller function of y, so this would be x equals, what do I want to say here, g1 of y, a smaller function of y, up to x equals g2, a function of y with larger values. Okay, so now, since it is this way, we want to first integrate with respect, when we do the D region, we're going to first integrate with respect to x. So again, so to get our iterated integral, we first do the z equals u1 of xy, z equals u2 of xy. Here's our function, and that's dz. But now, going outward here, we're going to now go first with respect to x. So dx, and then so I add a dx to the right, and now I do my integral sign to the left, and x is going to go from g1 of y to g2 of y, and then finally we end with d, in this case with dy, where y just goes from the numbers c to d. Okay. Again, we're going from inside a function of up to 2 variables, the next one a function of up to 1 variable, and then the outer one is just going to be numbers. Okay? Okay. So this is when z is seen to vary between these two functions. Well, we can then guess what our other two cases are. Our other two cases are when x varies between two functions or when y varies between two functions, okay? So let's consider this next one where x varies between two functions. So second case or second scenario, x varies between two functions of, let's see, the other two variables would be y and z. So I think I've got a picture here of this one. So this would be the second scenario. Okay. So this time, this thing is, the other one could be viewed as something that was standing upright. Well, this thing is like rolled over on its side, so to speak. Here's our x variable, and it's ranging between this lower function of y and z and this upper function of y and z. So that's what we have as our inside limits of integration. Then we have to integrate over this projection or this shadow of our region. Now this time around, our shadow area is going to be on the YZ plane. If you look at this thing, the shadow now it's taking this whole thing, it's projecting it down, and our plane is the YZ plane. So it's basically the other two variables, Y and Z. So we're going to be doing this double integral over D, which is in the YZ plane. Okay, so we'll start with X, then we'll be doing this double integral. So the same thing has to work out. We have to be able to get this as that iterated integral with 3 limits of integration in order to evaluate this. So in this case, okay, x goes between these two functions. Let's call it x equals u1, u sub 1 of y and z, and the top one is x is equal to u2 of y and z. And here's our function. And now we're initially integrating with respect to x. And then, let me just put this down here. We're then going to be integrating with respect to that shadow region D. Again, we've got to get ourselves an iterated integral, which means we need to sketch and analyze D, but this time D is going to be in the YZ plane. So sketch and analyze D, and this is going to be in the YZ plane. So draw out, for the most part, you'll be drawing out this YZ plane. And usually what you do is you have usually the lower letter of the alphabet goes on the horizontal one, the higher letter goes on the vertical one. What's that? Y going across and Z going up. All right. Okay. I won't go through both of the scenarios here, but let's just run through one of them. So say that we determine here that this region D is like this, okay, where y is going between two numbers, let's call it a and b, but z is going between two functions. The upper one, z, we'll say z is equal to h2. Now it's just going to be a function of the other variable y, and the lower one we'll say is h1 of y. Okay, so once we've got this down, then we can go and write out our iterated integral here. Okay, so let's start with the inside out. So therefore, we're going to do x here. X equals u1 of y and z, and up to u2 of y and z. Here's our function, and that's dx. And then in this case, we're going to want to, if it were this kind of scenario, we want to next integrate with respect to which of the two remaining variables? Z. We want to integrate with respect to z. We'll put your arrow in there, whatever it takes. Z goes from the lower function to the upper function. So z equaling h1 of y up to z equaling h2 of y, and then put your dz over there on the right. And then last of all, we have the other variable y, and this time y just goes between two numbers, a and b, and be sure to put your dy over there. And then we try our best to figure that out, okay? But that's what we have to set up, that iterated integral. Then the last case is where, let's see, we had z ranging, this one we had x ranging, the other one is if y is ranging between two functions. So I am going to beat a dead horse by going through this, all right? So here's the third scenario. Okay. Let me just show you a picture here, and I might just shorten this a little bit. Okay. So here, this is our region, our solid that we're integrating over E. And notice with this case, we have y ranging between two functions. This time they're functions of either of x and z, the other two variables. All right. And then this thing again casts a shadow onto in this case, the xz plane, the other two variables. So we're going to be doing this integration. We're going to start with y from the u1 to the u2. And then last of all, we have to do this integration with respect to the region in the xz plane. Again, we need to set it up as an iterated integral. Okay. So let me just do this with this particular one. Let's suppose when we analyze our xz plane, notice I have x here on the horizontal, z up on the vertical. Say we get something like this. Where z ranges from c to d, and this time x is going between two functions of z. So here we have, say, that x is equal to g2 of z, and the lower one would be x is equal to g1 of z. So the integral we would set up in this case is, first of all, we start with our y, going from u1 of xz to u2 of xz. Here's our function, and that's dy. And then in this case, we look at this and we see that we want to next integrate with respect to x. So I'm going to do my x next. X is going to go from what the lower one is g1 of z, and the upper one is g2 of z. And then last of all, we want to integrate with respect to z from c to d. Okay. So we have to get it set up like that. All right. So I think we need to look at some concrete examples here of how this works out. Let's start with this one. Evaluate the integral from 0 to 2, 0 to z squared, 0 to y minus z, of 2x minus y. Let me put that in parentheses. Let's see, we're doing dx, dy, and dz. All right. Now, this is a nice problem because it's already all set up for you as an iterated integral. Okay. Already set up as an iterated integral. Now, if you like, so notice here we're starting with x ranging from 0 to y minus z. That y minus z, that would be our function of y and z, our top function. Then y is, so x is connected with these, y is connected with those limits, and z is connected with those limits. So, and notice y is going between 0 and z squared. We have a single variable there. So we have, in this case, we've got a double variable, or let me put it this way, two variables in the limit. Here we have a single variable in the limit, and here we have just numbers on the outside. Now, if you like to, you can certainly set up your D region if you just feel compelled to do that, and I'll just go on and do it here, although it's not really necessary here. It's all set up for you. But D here, what do we have? Y goes from 0 to z squared. Z goes from 0 to the number 2. So here's our zy plane. Z goes from 0 to 2. Y goes from 0 to z squared. So it's going to be coming out like this. Okay, and this would be the region here over which we're integrating. Okay, let's go on and do this then. So, here. Okay, let's start from the inside out. So we do the inside one, 2x minus y. Now in this inside one, remember, y and z are treated as constants, because we're integrating with respect to x. So therefore, this first one, 2x, that's going to become 2x squared over 2. That's going to be x squared. Minus y is going to be minus y times x. All right. And then our limits then are x equaling 0, x equaling y minus z. And then let's just put in the two outer ones, 0 to z squared, 0 to 2, dy dz. Okay. So we have to do our limits, fill in our limits here. The bottom limit is 0, so that's going to drop out. So what we're going to get here, I have to plug in y minus z in for x here. So this is going to be y minus z squared minus y, and then I plug in y minus z there. And then again, it's over the limits here, 0 to 2, 0 to z squared. So of course I want to simplify that inside part here. So this is going to, let me jump a little bit to the chase here, that this is going to simplify as z squared minus y times z. Okay, FOIL it out and distribute. That is what it's going to simplify as. So then we go to our inside one, 0 to z squared of z squared minus yz dy. That's our next one. And then 0 to 2 dz. Okay. So now with this one, integrating with respect to y, so we're going to treat z as a constant. And it might not hurt to write that down on your paper just to remind yourself of that. All right. So the first one then, z squared, integrating with respect to y, that's going to be just z squared times y. Now here, that z is a constant, but y is my variable. So what am I going to get? I'm going to get, let's say, minus z times y squared over 2 when we integrate the y. And then our limits here are going to be y equaling 0 and y equaling z squared. And notice it's only because if if there's a mistake to be made, I'm going to find it somewhere. All right? So that's why I like to put those y equal and y equal just to remind myself that, hey, that's what I'm plugging in on my top and bottom so that you don't mess up on that. Do what you like, but that's what I tend to do here. And then let's write the outside one, 0 to 2 dz. Okay, so now we got to plug in. Okay, again, with 0, that's nice because my bottom limits just disappear. So the top one, I plug in y equals z squared. That'll be z squared times z squared. That'll be z to the 4th. And then what will my second term here become? Which one? Z to the 5th over 2. Because y squared will give me z to the 4th times z, so that's z to the 5th and then over the 2. Okay. And then this is then 0 to 2 dz. Almost done with this. Okay, now we're just left with z. This is z to the 5th over 5 minus z to the 6th over 6 times 2 is 12. And we're integrating from 0 to 2. Again, the zeros are nice. They'll just disappear. So I'm left with 2 to the 5th over 5 minus 2 to the 6th over 12. And basically, that's going to be 32 over 5 minus 64 over 12. And that comes out to, when we work that out, 16 over 15, right? This can be reduced. Let's see, 4 goes into 12 3 times, 4 goes into 64 16 times. So that's my answer, 16 over 15, right? Now, oh well, we'll see what happens. That's all I can say. It's Monday, we know what that means. That's the clock. Is everybody okay with that last example? I mean, at least that one actually was one of the easier types of problems because everything was all set up for you. This one is not quite so straightforward. We're asked to evaluate, okay, we're just given a triple integral over some solid E of z times dv. And then we get a description of what this solid is, where E is bounded by the planes. Okay, we're given a bunch of stuff. X equals 0, Y equals 0, Z equals 0, and finally, X plus Y plus Z equaling 1. All right. Okay. We have to fit it into one of our three categories here. I'm going to choose to see this as, well, you know what, actually what helps here with this, before we even do anything, It's not that hard, even for me, to draw this thing. We know, of course, we see here, it's bounded by all of these axes right here, y equals 0, x equals 0, and all that, all right? But then finally, what we have here is this thing, x plus y plus z equals 1. Well, if you look at it here, on the z-axis, if we have z equal 1, x equals 0, y equals 0, this point right here is part of that plane. Z is 1, x is 0, y is 0. Similarly, if I go down here on the x-axis, when x is 1 and y is 0 and z is 0, that's also a point on this plane. And then finally, if I go over on the y-axis, y is 1 and then x and z are 0, basically y is 1, x is 0, z is 0. Right, we again have a point. So what we have here is like this triangle that's tilting towards the z-axis here. This is that part right there. So this here is my solid. It's got 1, 2, 3, 4. It's a tetrahedron. It actually has 4 sides to it. All right, it's like kind of a skewed pyramid of some kind.
How do you get the L equals 1 if all 3 of those are not x?
What's in that?
If all 3 of those x equals 0, y equals 0, z equals 0, how did you get those points?
It's bounded by that. So z equals 0 means it's bounded below by the xy plane. X equals 0 means it's bounded by the yz plane. Y equals 0 means it's bounded by the xz plane, which this is like, look in the corner of this room, z, y, and x. And we have a little tilted triangle tilting, kind of fitting into that corner. That would be the plane. That x plus y plus z equals 1. So we're meeting all of our conditions. Were you concerned that we weren't meeting all of our conditions? Or?
I know, I just got confused.
Yeah, I thought there's got to be a relationship, and when you just look what it is on the different axes, it's actually not too hard to draw. All right. Now, the thing is, okay, let's see, I'm going to say, let's have this be my low z function, and then let's isolate z on the other side, on one side with this one, and so z is equal to 1 minus x minus y, and let this be my top z function. So I can do it that way. Top z function, bottom z function. So let's start this out. I can go from z equals 0 to z equals 1 minus x minus y, lower to top. Now remember, we are integrating something here, so I put in a z. And then this is dz. Now, I also have to then figure out, let me first start with just this double integral over d. We do have to figure out the limits of integration over that shadow of this space. So what is d here? Well, first of all, d is going to be on what plane? xy, the other two variables, is going to be on the xy plane. Let's see if we can draw it here. It's real important to do this. So we have our xy plane. Now, on the xy plane, what is our value of, and for any point on the xy plane, what's the value of z? 0. Z is 0 on the whole xy plane. So z is 0. Okay, what we have to find out is, basically, where does z equal 1 minus x minus y, let me phrase it as this, hit or intersect the xy plane? Well, any thoughts on how I could figure that out?
Zero y equals 1 minus x or 1.
Well, you're right. That is what's going to happen. But can you tell me how you got to that?
Z equals 0.
That's it. Here we said z equal to 0. All right, because that's where the xy plane is. 0 equals 1 minus x minus y. So we can say here, let's isolate y. So therefore, y is equal to 1 minus x. All right. Okay. So let's plot that. Y equals 1 minus x. When x is 0, y is 1, and then when x is 1, y is 0. All right. And this indeed is our triangle. This triangle right down here at the bottom in the xy plane. Okay. So let's set up our iterated integral now. We can go in either direction here, because this is what I have on my paper. I want to go with this so that I can watch myself. Oh, gosh. I'm going to do it this way. Integrate where y goes from 0 to, this line here we said was 1 minus x. Y goes from 0 to 1 minus x. 0, y equals 0, y equals 1 minus x. Well, let me put my inside integral here. Z equals 0 to z equals 1 minus x minus y. Here's, don't forget our function z. So we first have dz. Now if I'm then doing y, I'm going to put dy here next. And then finally, what are my limits then for x? Lower and upper limit for x. 0 and 1, right. We can see that from the diagram. Okay, so this thing right here, I can work with this now. Now that I've set up my 3 limits of integration, I can then proceed along and do it step by step and get my answer. Again, I just want to point this out, and then I'll shut up, that inside here, on the inside limits, we have both x and y, a function of both x and y. On the next set of limits, we only have a function of x. And then on the outside limits, we always have just numbers. All right? And then proceed from there with that one. Okay, that's a good enough spot to stop at. We'll continue.